We've been looking at the Fibonacci numbers. I did get a question from an earlier section, the pigeonhole principle. So let's go ahead and look at the question I had gotten asked from assignment 2.1, number 14. Now I answered this one in the other class too, so I'll make it larger and we'll talk about why the answer is what it is. So you have 7 pairs of socks, 7 pairs of black socks, and 7 pairs of blue socks. So 14 pairs altogether. Now you'll have a different number. We all have different numbers of sets of socks here. They're not all paired up. Instead, they're all mixed up in a drawer. Does anybody else store their socks like that? Yeah, guilty. Okay. It's early in the morning and you don't want to turn on the lights in your dark room. How many socks must you pull out to guarantee that you have a pair of one color? How about 2 pair? Or how about to get a black pair? So let's look at these different options together. So I have 7 pairs of black and 7 of blue. Move it down. Thank you. So I have 7 pairs of black and 7 pairs of blue, and like I said, you may have different numbers. So I have 14 pairs or 28 socks altogether. So when I go to pick out socks, if I want to get a pair, and I don't know what color they are because it's in the dark and I'm just pulling socks out randomly, we think about, well, how long could it take to get to those pair that match? So it could be I get a pair right away, but it might be that I get a black sock first, then a blue sock. And if that happens, then I need one more sock, because if I have one more sock, then it's going to be either black or blue, and that gives me a pair. So that I'll need to pull out 3, and that way for sure I'll get a pair out of it, if I can't tell what color they are because it's dark. So I might get a pair with 2, but for sure with 3 I'll get a pair. Now if I need 2 pair, again we go through the worst case scenario. So we might not get any pair at all on the first 2. Then I pull out another sock and it has to give me a pair. When I pull out a 4th sock, it might still be in with a pair that I had before. So I could have 3 black and 1 blue, or 3 blue and 1 black, and I still wouldn't have 2 pair. But then when I get one more sock, it has to make the case, I'll have to have 2 pair then. So I might get 2 pair right away with 4 socks, but I might have to take up to 5 socks before I get either 4 of those all the same color, or 2 of one color and 3 of another color. Or maybe 5 are all the same color, but if that's the case, then I still have 4 of the same color, so that's 2 pairs. So the last question is, what if I want to get a particular color? I want a black pair. So again, we go through the worst case scenario. How many socks could we pull out and not get a black pair? How many socks could I pull out and not get a black pair? Yes, I could. Yeah, I could pull out 14 blue socks and still not have a black pair. So we're going through the worst case scenario. So if I keep pulling out socks, and they're not black, I could do that for 14 times. But after that, if I pick 2 more, then I have to have a black pair in there as well. So if I want to be sure of getting a particular color of sock, I need to pick 16. I need to pick all the other color out and then 2 more. Now I might get a pair right away on the first 2, but again we're saying how many do you need to pick to be sure of getting a black pair. Anybody have any questions on that, or another question from the homework to go over? Okay. I made a note to myself to tell you why I don't use PowerPoints. There are PowerPoints that the author supplies to go with our text, but I do not use them because I think it's good if you write along with me, because I think then you remember better. And I think it's good that I write because that slows me down a little bit so I don't go too fast and you're still trying to think something out. We write it out together. It helps us both to pace ourselves and to remember what we're looking at. So we've been looking at the Fibonacci sequence in 2.2. The author's life lesson there is unexpected patterns are often a sign of hidden underlying structures. So we're going to be looking at unexpected patterns in the Fibonacci sequence. So first thing to do is to make sure you know how to write out the Fibonacci sequence. Who remembers how the Fibonacci sequence starts? What numbers did we start it with? Yes?
Well, can we start with like 1,
Mm-hmm.
and then like 1, 2, 3, 5, 8.
Good. Good. Yeah. So start with 1, 1, and then how did you get the 2?
Add 1 and 1 together.
Add 1 and 1 together. So keep going, please. Can you write the next numbers down until you have 15 Fibonacci numbers written out, and that will be a question that I would ask you on a quiz, so this will be good practice for that, okay? You might want your calculator. So that sequence goes on forever, but we'll just write down 15. You should have on your paper 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233, 377, and 610. We had been looking in class at the ratios of those Fibonacci sequence. We were taking a number in the Fibonacci sequence and dividing it by the number before and looking at those ratios. For example, we'll take the 610 divided by 377. We didn't get that far in class, but we know what that approximates because we did get to some earlier ratios. Who remembers what do these ratios come out to be approximately? Yes?
1.6.
Yay, 1.6. Good job. Let's see what it is to more decimal places. Let's get that to 4 decimal places here. 1.618 to 4 decimal places. We're going to look at some underlying structures here. It turns out that we can write these ratios with all ones. So we can write these ratios using only ones, and that's going to give us a look at the underlying structure that we see. So let's go ahead and do that. So first one, 1 over 1. That's pretty easy. That's just ones. All right, how about 2 over 1? Now I'm going to get a pattern here that will work not just for 2 over 1, but will work for 34 over 21 or 89 over 55. So the pattern I'm going to do is to split the top up. The 2, I'm going to write it as 1 plus 1 instead of a 2. I'm using the 1 from the denominator for the first number there. And then I'm going to continue in a pattern that I'll be able to replicate for bigger numbers. I'm going to make the fraction split up. So when you have a sum in the numerator and just one number in the denominator, you can split that into two fractions, which is still, I mean, 1 over 1 is 1 and 1 over 1 is 1. So this is just 2. This is still just 2. The 1 over 1 I'll write as 1. The first 1 over 1. The second 1 over 1 I'll leave because we're getting a pattern. So this is just 2, but we're writing it in a way that's giving us a pattern for these later ratios that we see. So let's go on to the next ratio, 3 over 2. So we're taking a number in the Fibonacci sequence and dividing it by the number before. And we're just going up through successive numbers, and we're going to get a pattern here. And each one of these we'll be able to write using just the number 1. So the 3 over 2, I'm going to break up like I did here. Okay, so I used 1 plus 1 for the 2 before. Now, since the denominator is 2, I'm going to write 3 as 2 plus 1. Okay, so because the denominator was 2, I wrote the 3 as 2 plus 1. Because that way I can split this up into two fractions again. Hopefully you had your lunch, because this is kind of a lot of arithmetic to think through. So we have the 2 over 2 plus the 1 over 2. Now the 2 over 2 is 1. So in our quest for 1s, we have a 2 over 2, which is 1. I'm going to change the 1 over 2 also. See how the 1 over 2 flips the 2 over 1? I'm going to write the 1/2 as 1 divided by 2 over 1. So I'm replacing the 1/2 with 1 divided by 2 over 1. Let's just make sure that's okay before we talk about why we'd want to do that. So let's off to the side, let's think about that. Why is that okay? So when you have a number on the top and a fraction on the bottom, do you remember how you simplify that when you have a fraction in the bottom of your fraction? You flip the bottom over. Okay, you invert and multiply, or flip the bottom over and change to multiplying. So when you have 1 divided by 2 over 1, that's the same as you leave the 1 on top alone, but flip the 2 over 1 to be a 1/2. So you just have 1 times 1/2. So that's what we do when you have fractions in the bottom of your fraction. You flip the bottom fraction over and multiply it times the number on top. So 1 times 1 over 2 instead of 1 divided by 2 over 1. So still a half, okay? We had a half here, and now we're writing a half in this way. Now you might wonder why we'd want to do that. Good question. Why would you want to make that complicated like that? Because we're getting a pattern that we want to keep working, and this pattern is going to allow us to take the 2 over 1, see that's a 2 over 1, and look how we ended up writing the 2 over 1. Follow your equal signs. We wrote the 2 over 1 like this. So I'm going to write the 2 over 1 as 1 plus 1 over 1. So I'm leaving the 1 and the 1 here, but the 2 over 1 I'm writing as 1 plus 1 over 1. Okay, so we're getting a pattern that we can use over and over as the numbers get larger. But again, you haven't done anything much. 2 is 1 plus 1. And what do we have here? 1 plus 1. So this 1 plus 1 is just that 2 right there. But we wrote it in such a way that we could follow the step before. We're going to do another one of these. Do you have any questions on any steps on this one? Yes?
I don't understand, I'm sorry, but I don't understand any of this. I kind of get how you got from 2 over 1 to the 1 plus 1 over 1, but
Okay.
I can't really follow it.
Okay. So you were okay getting over to here. Okay. Are you okay with this 2 over 2 becoming a 1?
I think so.
That's okay? Okay. So then this 1 over 2, we changed over to be a 1 on top and it flipped on the bottom.
Okay.
Because of this reason over here. When you flip it, when you have the fraction in the bottom, you flip it and multiply it times the top, and you get a half back. So this is still 1/2, but it's 1/2 written with a 1/2 flipped upside down and put in the bottom.
Okay.
And the reason we did that is because if you have a 2/1, we already figured out how to write that with just ones. So we're doing all of this to write it with just ones. We'll try another one and see if that helps, okay? We'll try another one. Okay, so the next one would be 5/3. Okay, so 5/3. So this time the bottom is a 3, so I'm going to change the 5 to be 3 plus 2. So I'm changing the top to be 3 plus 2 because the bottom's a 3, so that's how I know to use 3 plus 2. And then the next step was to make 2 little fractions out of that. So I'll put the 3/3 plus the 2/3. Like that. So that's how we add fractions together when the bottoms match. When the bottoms of the fractions are the same, we add the tops together. So we're going backwards. Usually you take these 2 fractions and add them to get this, but now we're going the other way. So whenever you have the top and the bottom of the fraction the same, that's a 1. So that's why we wanted to have 3/3, because that's a 1. So the 3/3 is a 1. And the 2/3, I'm going to do the same flipping thing that I did right here. Instead of 2/3, I'm going to write 1 divided by 3/2. I'm going to flip it. You can check that in your calculator if you want to. Another way to see that. So if you take the 2 divided by 3, you get 0.6 repeating. And if you take 1 divided by, parentheses, 3 divided by 2, you get the same thing. And again, it's because you would take this 1 divided by 3/2 and flip the bottom over and multiply it times the top. Well, the reason to do that is because then we can use the step before. So we're always trying to use the work we did before to help us out. So the line before, I'm going to use red now. We said what 3/2 is. Mm-hmm. We figured out, follow your equals, 3/2 is equal to this expression all in ones. So we figured out how to write 3/2 all in ones, and so I can use that to write this 3/2 all in ones now. So this is 5/3. It equals 1 plus 1 divided by 3/2. So I'm going to write the 1 and the 1 on top of the fraction bar. But now I take that 3/2 and replace it with that expression in ones because these are equal. I write 1. Let's see, make sure I get the number of ones right. 1 plus 1 over 1 plus 1 over 1. So we can keep doing this because we have a pattern established. We can keep writing these ratios. We split them up, get the first part to be a 1, take the second part and flip it under a 1, and use the line of work before to fill in what that is. And that way we can write what's called a continued fraction, a fraction that just keeps having more and more layers and written in ones. So continued fractions are a study in mathematics all by themselves. I had a whole semester just on continued fractions in graduate school. I can tell you it all like that. So no matter how far we go down these ratios then, even this one, 610 over 377, we could eventually get to this point where it's all layers of ones. So for example, what do you think the 101st Fibonacci, how many, I forgot, I put the B's, Fibonacci, okay, there. The 101st Fibonacci number divided by the 100th, there's only one B. I'll spell it right this time, okay. The 100th Fibonacci number, what do you think that looks like? A lot of ones, that's right. Let's use this to help us figure out what it looks like. Okay, so it'd be a 1 plus a 1 over 1 plus a 1 over 1 plus a 1 over, and then I'll put 3 dots because we don't want to write all those layers, right? But it would eventually come to an end. Okay, so it would eventually come to an end. We would have a lot of fraction bars. We can even count the number of fraction bars we have established in our pattern here and say how many fraction bars there would be. There would be 99 fraction bars. Whoops, another way here. So these Fibonacci sequence ratios can be written with a series of ones. All of this is to help us to get to phi. Remember what phi was? So phi was pronounced phi like at an ATM, but it's the Greek letter PHI. And phi was the ratio, the number that we approach as the ratio of these Fibonacci sequence numbers are going off into infinity. It was a number we got closer and closer to as we continued making ratios of one Fibonacci sequence divided by one Fibonacci sequence number divided by the number before it. And that number was about 1.6, but now we're going to find out what it is exactly. So phi exactly would look like 1 plus, it's going to look like this, only it's not going to have an end. This had an end after 99 fraction bars. Phi itself won't have an end because it will go on forever because the Fibonacci sequence goes on forever. So instead of putting dot, 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 and then going on to a finishing mark, there is no finishing mark for phi's continued fraction of ones. So this is a way to describe phi exactly. It might be argued that it's not a very descriptive way to divide phi. I mean, the 1.6 seems more clear what that is than this continued fraction of ones. So we're going to get a few other ways to define phi. So I want you to think about something here. I'm going to circle this part of phi in red, okay? So I have 1 plus 1 divided by this part I circled in red. And I'm going to ask you, what is this? What is this part I've circled in red? Now you've seen it today. You've written it in your notes today, actually. What is it? Yes? It's phi. Yeah, that's what you're looking for. It's phi. It's phi itself. This is phi. Look at that. If I covered this up and I just showed you that and said, what is that? After today's class, you'd hopefully say, oh, that's phi. It is. It's phi. So phi is inside of itself. Phi is the number that can be written as a continued fraction of ones, and it's also the number that's inside of itself. Phi is 1 plus 1 over itself, which I think is pretty cool. So there's another way to describe phi. Now we're going to solve this. This is an equation. Well, we know how to solve equations in math. So let's write this equation down again, and let's solve it for an approximate value of phi. So we were getting an approximate value of phi looking at the ratios of successive Fibonacci numbers, but we didn't go off to infinity. So this approximation of phi will give us the exact value if we were to go off to infinity. Okay, so we have an equation. To solve the equation, we first want to get rid of the fraction. This is just like if you had an equation with x's instead of phi's. So you could say x equals 1 plus 1 over x. And if you wanted to solve that, you would multiply both sides of the equation by phi. So that would give you, on the left, you'd have a phi times phi, which is phi squared. And again, that's just like having x squared. But phi is a special number, like pi is a special number. Phi is a special number, so it has its own name. So we have phi squared, and then this phi distributes. Okay, so we're solving for phi. We're solving for phi. So 1 times phi is phi. And then the 1 over phi times phi, those phi's cancel, and you get 1. So you have phi squared equals phi plus 1. This would be just like solving x squared equals x plus 1. So this is a quadratic equation. Who knows what a quadratic equation is? You've seen them before, right? It's on the, they have x squareds in them. Okay, so they're x squared. We have a phi squared. Who remembers what we used to solve the quadratic equation? Yeah, good. Yeah, so we learned the quadratic formula singing it to the tune of Pop Goes the Weasel. At least that's how I remembered. Did anybody else learn how to remember it that way? Yeah? Okay. Does anyone want to sing it for us? Oh. All right. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So I'm not singing it either, okay? But that looks familiar, right? Look familiar? All right. Well, we're not going to go through and solve it. I'm just going to tell you what the answer is. Tell you the value that phi turns out to be. Phi comes out to be 1. Let me make sure I have it right here. 1 plus the square root of 5 over 2. So that's the exact value for phi. So it's a special number. It has its own name, similar to the pi having its own name. And it's the number that's within itself. Its phi is 1 plus 1 divided by phi, because you have this continued fraction of 1's, and that part inside here is phi itself. Well, let's see what that is approximately. So your calculator will give you the approximate value, and it should be near 1.6. So if you have a scientific calculator, it can probably manage all of these steps at once. If you don't have a scientific calculator, you would go through in steps. So we're going to go through in steps just in case you don't have a scientific calculator. So first find the square root of 5. Okay, when you have your square root of 5 figured out, then add the 1 over here to it. Okay, so you have the square root of 5, and then you add 1, and take that answer and divide by 2. So I have about 12 decimal places. Your calculator still is not finding the exact value here. It is rounding off or truncating depending on your calculator. So I'm going to say approximately because it rounded off or truncated there. So we have lots of ways to express phi, and we explored that ratio as a continued fraction, so we could get to this point, phi is 1 plus 1 over phi, and then once we were at that point, we could find the exact value for phi. Now we did a lot of arithmetic here, and you might wonder, oh man, that was kind of hard stuff. What do I not have to know? Let's go through what you have to know. Okay, so I have a yellow highlighter, and you can grab a yellow highlighter. What you'll need to know for the quiz. Okay. So for the quiz, you'll need to recognize different forms of phi. You'll need to recognize the continued fraction form. Okay, the continued fraction of ones that goes on forever. You'll need to recognize this equation, that phi is the number that's in itself as in this form, 1 plus 1 over phi. You'll need to recognize phi as 1 plus the square root of 5 over 2. And you'll need to know the approximate value of phi. Just the 1.6 is fine, okay. So 4 things. If the math threw you, don't worry about it, okay? If that was like, I don't remember that stuff, that's okay. For those of you who do remember, it's kind of fun to see where things come from. Now the Fibonacci sequence we looked at in nature, the Fibonacci sequence has a number of applications. So I printed out a few from Wikipedia. Wikipedia is a good place to look at math. So there were a couple of economics examples on Wikipedia for using the Fibonacci sequence. There's just plain math problems, so that's what Hilbert's is. Here's another math problem that we're going to look at ourselves together. This is that every positive integer can be written in a unique way as a sum of one or more distinct Fibonacci numbers in such a way that the sum does not include any two consecutive Fibonacci numbers. This is known as Zeckendorf's theorem. So we're going to be looking at that more closely later. You don't have to write that down. And then there's a number of software applications that use the Fibonacci sequence, so I highlighted a couple that I saw. So all those 4 software applications. And here's an application in optics, and here again we see some economics. I thought it was interesting, though, this application in nature that comes next. So this application in nature is regarding the X chromosome. So Fibonacci looked at the Fibonacci sequence in regards to rabbits. You might have noticed that on your homework, pairs of breeding rabbits. Well, in a similar fashion, we have, it has been noticed that the number of possible ancestors on the human X chromosome inheritance line at a given ancestral generation also follows the Fibonacci sequence, and it traces through first a male's own chromosome of 1, and then from his parents, that came from a single parent, that X chromosome, and then it goes through where their parents came from, and you get the 1, 1, 2, 3, 5, and it's kind of an interesting application. Let's take a look at the Zeckendorf's theorem. So the author has two questions for this section because he knows it takes 2 class periods. The second question is regarding the Zeckendorf theorem that I pointed out on Wikipedia. Because not every counting number is a Fibonacci number, is there any way to express non-Fibonacci numbers in terms of Fibonacci numbers? How can you express non-Fibonacci numbers in terms of Fibonacci numbers? So let's go ahead and see how we can do that. So you'll need your list of Fibonacci numbers accessible when you do this. So this is a likely quiz question, and when you see it, you'll want to write down your Fibonacci sequence. I'll just put mine on the overhead here, and you can use those along with me. Okay, so the question is, how can every number, I'm going to say positive number, in fact, I'm going to say positive integer, be expressed as a sum of non-consecutive. How can every positive integer be expressed as a sum of non-consecutive Fibonacci numbers? Sum means adding. how can every positive integer be expressed as a sum of non-consecutive Fibonacci numbers? So there's a strategy for this, and we're going to look at the strategy. First, I'm going to get a biggish number from somebody in the classroom. Okay, so how about a number smaller than 600? How about between 100 and 600? Someone give me a number.
520.
520. Okay. So here's the strategy. We take our number, 520. We look at our list of Fibonacci numbers. That's why I set up to 600, because that's how far we wrote our list. And we look for the biggest number that's a Fibonacci number that's smaller than 520. So the biggest number that's a Fibonacci number smaller than 520 would be 377. Okay, so we write that down, 377. And then we have to see, well, what do we have to add to that? So let's see. 520 minus 377, 143. Okay, so now I look for the biggest number that's a Fibonacci number that's smaller than 143, and that would be 89, wouldn't it? Okay, so let me say plus 89. And now I see how much more I need. So 54 is what I have left, so I need the biggest number less than 54 that's a Fibonacci number, so that would be the 34. So I'm always looking for the biggest number I can. So 34, and I think that leaves 20, right? 20 more. So the biggest Fibonacci number less than 20 is 13. And that leaves 7. So the biggest Fibonacci number less than 7 is 5. And then 7... why did I write 7 down? That shouldn't have been written down. I think I was writing and talking at the same time. Okay, now I have no idea where I'm at. Let me add these all up. Okay, so we're at 377 plus 89 plus 34 plus 13 plus 7. 520. Oh, that's all? Okay. Oh, 7's not a Fibonacci number. That's why I had the 5 in there. Okay, so the 7 we write is 5 plus 2, right? Those are Fibonacci numbers. Okay. So every number can be written as a sum of non-consecutive Fibonacci numbers as long as you take this strategy. Always pick the largest possible and then work your way down. So let's try that again, because this is another quiz question that I'd likely ask you. So someone else give me another number smaller than 600. Yes?
400.
400. Okay, 400. So what would be our first choice then? What do we pick first?
377.
Good, 377. The biggest number we can that's a Fibonacci number and smaller than 400. So that leaves us with 23 to go. So now what do I pick?
21.
Yeah, 21. The biggest number I can pick that's smaller than 23, that's a Fibonacci number yet. And that leaves 2. 2 more. So 377 plus 21 plus 2 adds to 400, and that's all non-consecutive. Consecutive means right next to each other, right? You can spend some time thinking about why they can be non-consecutive in this fashion. Why this works. Okay, one more. This time you'll try it on your own though. Okay, so somebody give me one more number here. Who had a number? Yes?
555.
555. Okay, go ahead and work that out. And while you're working that out, I'm going to hand out some toothpicks. And we're going to play a game, Fibonacci Nim. Nicholas, do you mind working out in the back there and handing out little bunches? So if you give everyone around 10, just approximately, they'll only get in pairs every. I'll start with did you pick out the biggest number for that list up there? That's smaller than 555? Yeah, and then I would use your calculator. 5, 55. So now what do you pick for the next one?
The next highest number.
Which one is that? Good. So did you just pick like around 10, just a little handful? Any number. So the biggest one in our list we can grab is 377. So we'll take that away. We'll take out our calculator and subtract that. We get 178. So now the next biggest number I can take is 144. And that leaves 34. Oh, and 34 is a Fibonacci number, so I'll put that on my list. Okay. And then I double check. 377 plus 144 plus 34 is 555. Does anybody have any questions on that? Yes.
Wait, so for the last one, what did you do with 144 side?
Let's see. So we take the 555 and we subtract off the biggest number we can, 377. Whoops. And that leaves 178. So I look at my list and 178 would go in here. So I'm going to take 144 away next. So then I say minus 144, and that leaves 34, and 34 actually is on my list. So that's why I picked 34 next.
Wait, so you get, okay, so you subtract 377 from 555. So you put 144 in there, but you subtract 144 from 178, and then you get 34, and you also put 34 in there? 34, I could say minus 34. But it was right on my list, so I knew I'd get 0. So whatever the answer is here, I'm looking for the biggest number in my list that's either that number or smaller. If you don't have a calculator out, it's kind of hard to see it. So I'd be glad to work with you one-on-one on this too, or so would Nicholas. Okay. Well, this is actually how we play Fibonacci NIM. So you can play Fibonacci NIM in pairs. So get with a pair of people, put your toothpicks together, okay, and we're going to play Fibonacci NIM. And the first player is always going to pick this number. The first player is always going to take their number of toothpicks, split it up in a list here, and split it up into a sum like we did here, and pick the smallest number. So that will be the winning strategy. The first player is always going to be taking their toothpicks and splitting it up. So get together in pairs and we'll work through a game together. Okay? All right. So I'm going to get some toothpicks too, if there's any left, hopefully. First row, can you please work with the second row? Third row, can you work with the fourth row? Thank you. Thank you. And can you go around and help people get in pairs if they're not? Nicholas will help you get in pairs if you're not in pairs, okay?
So the Fibonacci nim is a game that we play with toothpicks. So once you have a pair, put your toothpicks all together. Okay, so are you two working together? Yeah. Can you two are working? Wait, you two. So and you two are working together. Okay, good. And then you need one more person, right?
Yeah.
Okay. Let's see.
Take another one.
Okay.
And then you two work together. You know, it might be easier if you two work together than you two work together. Would that be okay? Because you know what? Turn around. Okay, so you two, and you two, and yeah. So Mariah, do you have another person that's by themselves?
I just have.
Oh, so you can work with Nevada, is that right? Okay, so you can turn around and work with Nevada. And then, can you arrange people in back there, Nicholas? So we'll have, okay, it looks like Olivia and Tabitha can work together, right? Okay. So, put your toothpicks together. Everybody consolidate toothpicks and put them in groups of 5 so you know how many you have, because it's a little hard otherwise, like to keep track of toothpicks if you don't have them in groups of 5. This is where you're like, oh, I hope he didn't give me too many toothpicks. Okay, so put your online students, Q-tips work pretty good at this. So however many you have is fine. I'm going to have this many. Just so they're grouped up in sets of 5 so that you can keep track. Now I'm going to show you the strategy so that you always win, but first I better tell you what the game is, right? It's a toothpick. You ever play a game where you pick up stuff and the one who picks up the last one wins? That's what this is. Oh, I've not played spoons, but I bet you do. You pick stuff up and the one who picks up the last one wins. But the rule is, here's the rule. When you pick up sticks, you must take at least one stick, but no more than 2 times the number of sticks the previous person took.
What?
Yeah, right? Okay, you take your sticks. You have to take 1 stick, but you can't take more than 2 times the number of sticks the previous person took. So if the person before you takes 3, you can take between 1 and 6. If the person before you takes 5, you can take between 1 and 10. Okay? Okay. So the first person's going to win, though, if you follow my directions. So first of all, first decide who's going to be player 1 in your group. You'll each get a chance. Okay? Okay. Now player 1, off to the side, write down your sum like we did up here. So write down your sum. Mine's 37, so I'm going to write 34 plus 3. You have your sum written out, player 1? All right, now you're ready. Player 1 can win if player 1 does this on every turn of theirs. Now, player 2, you be on the ball, because if player 1 messes up, player 2 can snatch the victory away. All right, so I'm player 1, so I made this sum, and I'm going to take away 3 because I made this sum. So, so you take away yours. Player 1, take away your amount, okay? Take away this amount, okay? Or whatever yours was. Don't use mine. Use however many sticks you had in your sum. Okay. Now player 2 can pick up to 2 times as many as you took away. So my player 2 could pick up to 6. Nicholas, you be player 2. Tell me how many to take away. You can take up to 6. Okay, 6 it is.
Up to.
Okay, so player 2, did you take your sticks away? Player 2, pick up to 2 times however many player 1 took. If your player 1 only took 1, you can only take 2 or 1. Now player one, you got to be on the ball. You have to do this again. Okay, so now player one has to count again. So player one counts again, and again picks the smallest number on their list. If you keep going like this, player one can win. All right? But if you lose your arithmetic, player two can snatch the victory away. Take a picture of this. This is your class activity.
Oh, okay, yeah. All right, you're right.
Yeah, you're right. I forgot that was a rule. You can't start with
She won, yeah, that's how it works. 5 steps.
No, everyone take up your
Wanting to follow what she lost.
Anybody else? Raise your hand. You start.
I picked up 1 and I picked up 3 and I picked up 5 and so I up to 2 times the amount.
You can pick up double the amount, right?
Yeah, I somehow lost.
Yeah.
So she only did 2.
That's okay.
Can you pick up double?
No.
You can pick up
How does it?
How did I win? How did
I don't know. Let's try it again.
Alright, I'm player 1, right? 5, 10, 15, 20.
Yeah, it's very
I've done that.
23. Up to 4. Anywhere in between.
Whoever takes the last step wins. Take a picture just at some point. It's your canvas activity.
I know.
The one who takes the last toothpick wins. And the second player can take up to twice as many as the first player took. And then it keeps going like that. So make sure you get a picture of this uploaded to Canvas. I'll see you in class on Wednesday.
Right. 13 plus 5. 13 plus 5. 15 plus 1.